Okay, so in this video, we're going to learn how to solve trigonometric integrals. And what is the big picture? What is happening when you're solving a trig substitution integral? The gist idea is that you need to substitute, that's where the name comes from, substitute this expression. Everything you have in terms of x needs to be in terms of theta. Now, how do you do that? How do you get rid of x? And then how do you determine what is x equal to in terms of theta? What is dx equal to in terms of theta? How do you go from x to theta? And can you even do that? Can you do that always? No, not always. You have to spot Pythagorean theorem there. And you have to see that there's an equation for a right triangle sitting there, where one side is this, the other side is that, and the whole expression, this whole expression, the radical, is the third side. If there was a circle equation, then you couldn't do the trig substitution. Okay, and even bigger, zooming out even more, a bigger idea that's happening here is that you're trying to calculate area under the curve. And under what curve? Under this curve, under the curve of this function. So what type of a function is that? And do I need calculus? Maybe I can get away without. So you put this function in Desmos and see what it looks like. Okay. And then this is how it looks like. Okay, I don't need that whole thing. I need from square root of 3, which is 1.732, to 2. So I just zoom in, take a screenshot, put it in my notebook, and start thinking about it. Okay, so this is the really big idea that's happening. As long as you accomplish the task, which is to calculate area, when you have a definite integral, they are asking you to calculate area from, and these are x bounds because you know that, because you have dx. Whatever you have here, these bounds have to be that variable. And so square root of 3, and then this is 2, okay? So as long as you can accomplish this under this curve, right? So this is the area. I mean, however you can do it. Unfortunately, there's not that many ways that you can do it. The only reason you need calculus here instead of just good old math that you knew from school is because of this curved line. Okay, if this was a simpler shape, and what would make it simpler? If this was a line instead of a curved line, then you know how to calculate areas of simple shapes like triangles, rectangles, squares. The only reason that you need student loans to calculate this area is because this is a curved line, not a straight line. Okay, so I'm going to calculate a ballpark of this rectangle. Could have gone with a triangle, but I'm just after an approximation, and both of them would do the job. So the width of this rectangle is 2 minus 1.732, and that is 0.268. And the height of this rectangle is, looks like it is, 0.5. Okay, and area is width times height, and height happens to be 0.5, which is same as dividing by 2. So width divided by 2, and that is area of this rectangle. That is 0.134, right? So I recognize that here I am calculating extra area, and I don't need that because they only asked me for this area under the curve from square root of 3 to 2. So some less than this should be my answer. So I guess what I should be expecting is approximately 0.1. If I get in that neighborhood, final answer, I'll be happy. So what happens in a regular trig substitution examples is that you translate the x expressions into theta expressions. You solve it using trig because this integral is impossible to solve in terms of x, and then you go back to x. The final answer is in terms of x. But here you don't have to do that because this is a definite integral. meaning the answer should be a number, a scalar, because it's like a two-dimensional shape. It's the area you're calculating, right? Don't forget that that's the big picture thing that's happening. I'm also going to show you the area of the trigonometric function that you're going to get from this and show you that it's the same area. So the analytical part of this is going to work out, obviously, but so does geometrical part of it, so that we have math and not just like disjointed kind of ideas that are not united through meaning. Okay, so let's do the translation. Let's do the trig substitution. Let's do the calculus part here. So I have a little template. So first let's put this integral, original version of it here, so that we don't forget what we're trying to translate, right? So that's the integral that we were given. And I have this template. Let me move this up. I have this template because these are all the things that you're going to need to do when you're presented with trig substitution integral. How do you know you have a trig substitution integral on your hands? Because this integral is extremely difficult or impossible to solve in terms of x, therefore you need something, and that something, this expression is telling you, has to be trig substitution, because right here, this is a triangle going on. But what triangle? Which triangle? There are 3 versions. So you need to assign and label the sides of this triangle correctly. If you incorrectly label the sides of the triangle, the world is going to end. Okay, so what do I need to translate? Well, I need to translate everything that is in terms of x. That expression, curious to know what that is in terms of theta, curious to know what x is in terms of theta, and dx in terms of, so that's my task list, okay? So when I say ingredients I need, those are the ingredients that I need, okay? So first, let's label the triangle. For the purposes of labeling the triangle, you can just look at this part of the integral. You do not need the entire integral, and that's helpful. So we're just looking at this portion of it, okay? Now, one thing that you know for sure is what is the hypotenuse. The other 2 sides, they're kind of arbitrary reasons why they have to be that, but there's no arbitrary reasoning behind what is the hypotenuse, because of the Pythagorean theorem. Pythagorean theorem says that this side squared, length of that side squared, this side squared, you add that equals to the hypotenuse squared, okay? So then how do you find, let's say, this side? You subtract from hypotenuse squared this side, right? Or how do you find this side? You subtract from hypotenuse squared this side from hypotenuse squared. You never ever subtract anything from one of these sides, ever. You're never going to see a minus sign, and before that is anything other than hypotenuse. That comes from Pythagorean theorem. It's very much a fundamental reason why whatever comes before minus sign has to be the hypotenuse, okay? This is not some bogus reason. Now comes the bogus reason, okay? This is how I remember it. The vertical side likes to be free, meaning likes to be a variable, does not want to be constricted to a specific number. It wants to be able to take on any number. So if you assign this to be x, then it can take on any value. But x is taken. The next best thing that the vertical side wants to be is this entire expression itself. There are 3 versions of these triangles. The vertical side is always going to be x in 2 cases, and it's always going to start with x. Maybe you can remember it like that. And the base of this triangle is always going to be either a or start with a squared. A is a number. Okay, there's another little trick. Don't make a mistake and say that this side is 3. It's not. It's square root of 3. Because square root of 3 squared gives you 3. And when you're labeling the sides of the triangle, make sure that either all of the sides are squared, so you have x squared here, you have 3, and you don't have this squared part, that's correct and kind of matched. And also, I like to go with none of them are squared. But don't miss and match them. Don't say this is x squared, then this is square root of 3, and this is square root of... No, some are squared and some are not. Don't do that because you will make a mistake, because the next step, I'm going to use these sides that I have just labeled, okay? So we know what we need. We need to translate this expression. We need to get these expressions in terms of theta. Now, how do I do that? There's a way to do that. There's 6 different possible ratios of 3 sides of the triangle, right? And those different ratios are your trig functions, okay? So there are 6 total. There's 3 original and 3 reciprocal. Whichever is original, that's up to you. Okay, so you choose the ratio that suits you. Now, what do I need? I need this side. And that side, for me, happens to be opposite of theta. Remember that theta is the star of the show here, because trigonometric functions are features of angles, not of triangles, okay? This side here on the circle, you kind of draw that there so that your eyes can see a triangle. But anywho, so this side is what you need. And that is opposite side. Now, you go to your ratios. Which ratio includes opposite? Well, there are 4 of them. Which one should I choose? Remember why you're doing this. This is why you need to know what you're doing at all times. You're trying to get rid of x. You're trying to write everything in terms of theta. So obviously, I would love to connect that side to a number, and I would hate to connect this to another x expression, which I'm trying to get rid of. Okay, so I'm gonna choose my ratio wisely, and I'm gonna say, also I would like the opposite side to be at the top, so I don't have to flip anything, and this one fits that requirement, okay? So this is tangent theta is always opposite side over adjacent. In our case, in our little triangle, that is opposite, and opposite to who? Theta. If theta was here, opposite would be this side, right? So it's all relative to theta. Okay, that's tangent theta. But I want to express this explicitly, so I'm going to do an extra step, one more step, to write down expression for that, because I'm going to need that. I'm not going to skip that and make a mindless mistake for that silly reason. No, no. Okay, now is my favorite part. You put a tick here because you have already accomplished this part of the task list. You have this expression in terms of theta, and to the right side of that expression, there are no x's anymore, just thetas. That's exactly what we wanted. Next one. Now let's express x. The same way, we're gonna go about it the same way. So that's the hypotenuse, remember? So hypotenuse, again, involved in 4 ratios. Which one do I choose? Trying to connect it to a number, definitely not another x expression. And it would be nice if it was at the top so I don't have to flip it. So secant fits that profile. Okay? Secant theta is always hypotenuse over adjacent. In our case, that is x over square root of 3. Okay. Let's express x explicitly, because that's what I was after. Again, my favorite part. Put a tick there as well. Now the final thing left to translate is dx, and I can't do that because I have x. So what is a derivative of x? Well, derivative of secant, if you don't remember that, that is secant theta, tangent theta. And then you keep the coefficient. Tangent theta. D theta. Don't forget d theta because this is calculus 2. You're going to need that d theta. Okay, so that felt great. So we did everything we needed to do. So we translated this integral, and now we have a totally new integral, right? I'm going to write that in the denominator, this in the denominator, and dx there, this whole thing for dx. That's interesting. But I can't have a d theta integral and have x bounds. I need new bounds. And how do I get new bounds? With O bounds. But exactly how? Do I have a relationship between x and theta? Yes, I do. Then if I have that, I have a recipe. How to get theta from x is 2. X lower bound is square root of 3. From my relationship, I can obviously say theta equals to arc secant x over square root of 3, and then put x upper bound instead of x, and the lower bound instead of x and c. But if that is confusing, arc secants, maybe this will be easier, maybe, okay? So you say x over square root of 3 equals secant theta. Now to find the upper bound, let me write that pretty. To find the upper bound, you first put in x upper bound, and you're going to find theta upper bound. You ask a question here that sounds like this. Secant of what angle equals to 2 over square root of 3? If you're not familiar with secants, remember, it's 1 over cosine. Remember, cosine of some angle is square root of 3 over 2, flipped of what you have here? Well, that angle is 30 degrees, but this is trig in calculus 2. All angles are in radians. So translate that degrees in radians. 30 degrees is pi over 6. So theta upper bound, is pi over 6, okay? And I'm going to label this. This is theta upper. I'll just put up. Okay, so now I'm going to say lower bound instead of the upper bound, and that was square root of 3. And ask the same question. Secant, and by the way, these get canceled, and this is 1. Secant of what angle gives you 1? Cosine, when is cosine 1? When angle is 0, right? 0 in degrees is 0 in radians, luckily. So that is 0. So theta lower bound is 0. That's the theta lower bound. Now I have translated this original integral, and then I'm going to show you how you write that. New lower bound, theta lower, 0. New upper bound, pi over 6. Then this part was that expression. Then divided by, or times dx, and dx equals to all of that stuff. That's fine. And all of that divided by x. And what is x equal to? You look in your neat translation, kind of created a little dictionary there, didn't you? Okay, now expect things to get canceled because usually they do. It's just 1 secant. Okay, what you ended up with is square root of 3 comes out of the integral. One of that didn't get canceled because that's just constant. So I bring that out of the integral. What I'm left with is tangent square theta. This is Calculus 2, you need d theta. So all I need to do now is take this integral, calculate area under that integral from in that range, multiply it by square root of 3, and hope that it will be same as this area. Okay, because analytically, I did all of that and then translated this expression into this expression that got reduced to that expression. So analytically, I didn't make a mistake. Geometrically, this area better be this area in this range times square root of 3. Otherwise, we don't have math, we have some type of astrology. Okay, so let's see if that happens. Okay, let me just show you that tangent square theta is a periodic function, and it is from here to here that you're interested in. So I'm gonna remove that and put it in a zoomed in version. And here is the little calculation of this rogue math before calculus math. I'm calculating this area right here, okay? And multiplying it by square root of 3 and seeing if it is within the same ballpark. And it is, and it was very close. 0.02 was the difference between them. So that's fine. So there it is if you want to screenshot it, but you can see it on Desmos, and this area times square root of 3 is this area exactly. So this is why we can do this, and this is why this is a legit thing to do and not some like weird thing that was invented. And I think that this is not shown in calculus classes, so you're like, what am I doing? Is this even legal math? And it is, and I think it's beautiful to see that work out. Okay, so now I'm going to just, since I don't know what is integral of tangent square theta, I'm going to rewrite that. And tangent square theta equals to this expression. This is a similar trig identity to cosine square x plus sine square x equal 1. And this relationship comes from that. Okay, so now I do know integral of secant square theta, that's tangent theta. Because derivative of tangent theta is secant square theta. And integral of 1 times d theta, that's just theta. Okay. Now, fundamental theorem of calculus. Everywhere you see theta, put in upper bound minus lower bound, and done. That's upper bound minus, now put in lower bound, done. Okay, a little bit of analysis. Tangent 0. Tangent is sine over cosine. Sine 0 over cosine 0. Cosine 0 is 1, but sine 0 is 0. So 0 over 1, that's still 0. So that's 0. 0 is 0. And so that whole thing is 0. So all I have is square root of 3. And tangent pi over 6 is sine 30 degrees, pi over 6, over cosine 30 degrees. So 1 over 2 over square root of 3 over 2. So 2's get canceled, and all you're left with is 1 over square root of 3 minus pi over 6. You can't do anything about that, okay? Put that square root of 3 inside the parentheses. You get 1 here, and you get square root of 3 times pi over 6 here. Put that in your calculator, and you're gonna get 3, 1, maybe? Something like that. Yep. So that is very close to 0.1, which is something we predicted initially. So this is useful because if you go through all that solution and you get your answer to be 700, you know you made a mistake. So we got the answer that was very close, but remember, we never really took this integral. We took this integral effectively. But this expression equals that expression, analytically as well as geometrically. So that was beautiful. So this is your final answer. You can box it and feel proud because this was quite a deep problem. And I think if you truly understand what's happening here, you learn a lot, hopefully. Okay, bye.